4. This was 1, 2, 3, 4. Number 4, this is a crash problem. Okay, I have two girls, and they each weigh 500 newtons. Okay, now remember, weight and mass are not the same thing. So, oops, I need the pen. Weight is equal to mass times gravity, which means that mass is equal to the weight divided by gravity. So if I want the mass, I'm going to have to take their weight, which is 500 newtons, and divide it by gravity, which is 9.8 meters per second squared. And can someone punch that in their calculator for me? It's going to be around 52 kilograms. $51.02. Okay. So we'll put in 51.02 kilograms. So that's the mass. Okay. Now they're riding in this car, and the car is traveling at 20 meters per second. One girl's wearing her seatbelt, the other girl's not wearing her seatbelt. Now the car's involved in an accident, and the girl with the seatbelt is brought to a stop in 0.12 seconds. The other one hits the dashboard, and it brings her to a stop in 0.008 seconds. All right. So we know the mass of both girls. We also know the change in velocity for both girls, because the car was going 20. It's going to go down to 0. So the change in velocity will be 20 meters per second. Okay. So impulse, you guys, we learned was two different things, or we could think of it in two different ways. We could think of it as the change in momentum, which is mass times change in velocity. We can also think of it as the force applied to the object times the time that the force was applied. So for the first part, it says, what is the impulse exerted on the girl wearing her seatbelt? We know the mass and we know the change in velocity, so we'll want to use this equation. So this is part A, right? So the impulse is going to be her mass, 51.02, times her speed, which is 20. If I do my math right, I think that is 1020.4. Can someone check that for me? 1020.4. Okay. And the units would be, kilograms meters per second. I was going to write something different. So that is the impulse. That is the change in momentum, 1020.4. Now, let me ask you this question. Does the girl who's not wearing her seatbelt, does she have a different change in momentum? Meaning, was her mass and her change in velocity different? Type yes or no. Type yes if it's the same, or no, it's different between the two girls. If I don't see it, I'm going to assume that you're not in our meeting. So it's different. They have different. So I want to ask this question. How could they have different, they have the same mass, they're in the same car, so they have the same change in velocity. Doesn't her impulse have to be the same? M delta V, whether she's wearing a seatbelt or whether she's not? It has to be the same, you guys. I have a feeling everybody just started typing that it wasn't the same because one person did it and everybody followed, right? But it is the same, okay? Whether she's wearing her seatbelt or whether she's not wearing her seatbelt, the impulse or the change in momentum is the same. Now, what's going to be different between the two is the force. So the girl who's wearing her seatbelt is going to have a different force than the girl who's not. Why? Because the girl who is wearing her seatbelt, she had a stopping time of 0.12. The girl who wasn't wearing her seatbelt, she had a stopping time of 0.008. And remember, we talked about this yesterday. If the stopping time is bigger, the force is smaller. If the stopping time is smaller, the force is bigger. So if I go back down here, this would be C. What's the force acting on the girl with the seatbelt? Well, I know the impulse. The impulse is 1020.4. I don't know the force, but I do know the time. That's 0.120 seconds. Now to get 0.120 on the other side, you have to divide both sides by 0.120. Those will cancel. And can someone tell me what that force is going to be? It's going to be fairly large. Nobody? Oh, there we go. So it's 8,503.3. 8,503.3 newtons. Okay. Now, if you translate that into pounds, it's a lot of pounds, right? This is a big force. But I think that she can probably survive this crash. She's just not going to feel good afterwards. Now, the girl who hits the dashboard, I'm not feeling very good about this because we have 1020.4 as a change in momentum equals a force times 0.008. So now to get the force by itself, I have to divide both sides by 0.008. What will that equal? You guys can check my math, but I got 127,550 newtons. Okay, I got it right. So, you guys, this would be equivalent. This is over 30,000 pounds of force. I don't think she's going to survive, right? She is not going to survive this. This is why we have seatbelts, right? We have seatbelts because they keep you in the car and they also lower the stopping time. If you hit something hard, you're going to have a very short stopping time and it's going to have a very bad result. Okay. So that was number 4. Are there any other ones? Do you want me to pick one? I'm going to pick, I think this is number 2. Number 2 says this. I have a 60-gram golf ball. So the mass here is 60 grams. Now, we never use grams, so we got to convert that. You divide it by 1,000. Move the decimal to the right 3 places if you remember it from chemistry. So that'll be 0.060 kilograms. Now the ball leaves the face of a golf club with a velocity of 75. Can someone tell me how fast golf balls are going before you hit them? This is not a trick question. Someone type it in the box. They are going 0 meters per second, right? So they start out at 0 and then it ends at 75. That means the change in velocity is going to be 75 meters per second. So I know the mass of the golf ball and I know the change in velocity. Now, the club exerted an average force of 30,000 newtons. I want to know what was the time of impact. So this is one of those cases where I'm the one applying the force and I'm trying to apply the force for as long as possible. This is one of those follow-through problems from yesterday. So remember that impulse is equal to force times time. Impulse is also equal to mass times change in velocity. So what that means is force times time equals mass times change in velocity. When we do our simulation today, you'll be using this. It's this type of problem, all right? So you'll be using this setup. Our simulation, instead of a golfer, it's a hockey player hitting a puck. So this is the equation I'll use. Ft equals m delta v. Make sure that you have all of these written on your equation sheet. And the force, we said that is 30,000. The time, that's what we're looking for. The mass, 0.0, oops, 0.0, the mass is 0.060 kilograms. And then the velocity, change in velocity, is 75 meters per second. So let's just do the arithmetic part of this problem. I have 30,000 times t. What's 0.06 times 75? Is it 4.5? Yep, okay, 4.5. My mental math is still doing okay this morning. So then I got to get rid of this 30,000. So I have to divide both sides by 30,000. And these 30,000s will go away. And that leaves me with 4.5 divided by 30,000. That I cannot do in my head, you guys. It's going to be a really small number. Uh, 0.00015. So, does that make sense to everybody? We're setting up force times time and setting it equal to mass times change in velocity. Now, before I cut you guys loose to do our little simulation lab, is there any other question you'd like me to do? Number 6. Okay. So this was 4, 5, and this is 6, right? Would have been helpful to me to number them. So number 6, I have a baseball. Okay. The mass of that baseball is 0.145 kilograms. And the baseball is traveling 20 meters per second through the air. And then a person wearing a glove is going to stop the ball. All right. So the change in velocity is going to be 20 meters per second. Started at 20, went to 0. Okay. Now, this person with the glove, he has, we're going to label this time with a glove. All right. He stops it in 0.15 seconds. And I want to know, what is the stopping force? So this would be part A. All right. I am going to use the same equation. Ft equals m delta v. All right. Now, I don't know the force, but I do know the stopping time, 0.15. I know the mass, 0.145 kilograms. And I know the change in velocity is 20 meters per second. Okay, so we can do the arithmetic part of this. F times 0.15 equals 20 times 0.145. I think that will be 2.9. Can someone confirm that with me? Okay. And then I have to get rid of the 0.15. So I'll divide both sides by 0.15. Those go away. And 2.9 divided by 0.15, I can't do that in my head. I got it to be 19.3 newtons. Can someone confirm that with me? Okay, got it right. So now, if you've ever played fast pitch softball, or you've ever played baseball, you know that you wear a glove. That glove is most of the time it's made out of leather. It's cushioned, right? And what that cushioning does, remember, it does not absorb the force. It makes the force less by increasing the stopping time. All right. Now here, if I barehand the ball, there's going to be a bigger force. Why? Because when the ball hits my hand, there's a shorter stopping time. So let's do the part B. I have the same force, but the time barehanded, we'll just put it as the time for just your hand is 0.02 seconds now. So I have the force times 0.02. That's going to equal 0.145. It's the same baseball. Times 20. It's the same baseball coming to the same stop. So this will be 2.9 again. But now the time is 0.02. So to get rid of that, I'll divide both sides by 0.02. And 2.9 divided by 0.02, that will equal 145 newtons. So a significantly higher force. And this is why, like, if you see someone barehand a ball, a hard hit ball, a lot of times their hand hurts afterwards. Sometimes you'll see it in professional games and then they'll have to shake it off. It's also why if you get hit by a pitch, that hurts. Because depending on where it hits you, it can come to a stop fairly quickly. All right? Now, there are places where it'll hurt more than other places. So let's say that you weren't wearing a batting helmet and a baseball hit your skull. I'm sure you guys can figure out that your skull, because it's harder, the ball is going to stop in a shorter amount of time and the force will be higher, right? So it's very dangerous to be hit in the head with a baseball if you're not wearing a batting helmet, if it's being pitched at 90 miles per hour. Now, if that ball hits you in the meat of your thigh, or a lot of times you'll see, people actually get hit in the butt, right? There you have muscle, you have fat, you have all kinds of soft tissue. So the ball comes to a stop in a less amount of time. Now, it's still going to hurt. It'll probably still leave a bruise if it was thrown at 90, but it's not as dangerous, right? Why? Because the force is actually smaller, right? The force is going to depend on the stopping time. And it'll stop much quicker bouncing off your skull than it will bouncing off your thigh. Does that make sense to everybody?